Continuing with class 14, here's another example out of Bornacki. This is his example 4.4, where we're using a nozzle. We just did a heat exchanger, and now we're doing a nozzle. Nozzles are useful in lots of different pieces of equipment. Quite often we'll have a converging nozzle and then have a diverging nozzle, and sometimes we'll call the diverging part a diffuser, right? So and this is also called a venturi tube. It's an important piece of equipment, and we'll see that we can actually generate a vacuum by having like a little tube that comes up from right here, and we can use this to we can actually use that to remove air, remove water, anything. You could just is sort of like a vacuum kind of thing. So by throwing some flow of fluid, it could be air, it could be liquid, we could draw up something right here, and then it could go along with it, and it could carry it away. So it's kind of a useful piece of equipment. Also, like one is an important element to a carburetor, which obviously a lot of cars and trucks are now use some type of fuel injection, whether into the flow stream or directly into the cylinder. But carburetors are still a useful thing that you'll see in like lawn mowers and that type of thing, and old cars, carburetors. So it's a venturi tube is an important thing to know about. So we have steam coming through this particular one, and here I'll even tell you there's actually one right here is the air ejector. Right here, this is actually the air ejector, a cooler right here, but an air ejector helps to remove gases that you don't want. There's steam inside the condenser, but there's also can be some gases entrained in the condensing liquid, and that's what the air ejector does. It ejects air. Anyway, so that is a type of venturi tube. Interestingly enough, it creates a vacuum. And so anyway, and it's steam run. That's what brought that up. So we have 600 kPa, 0.6 megapascals, and 200 degrees Celsius enters this insulated nozzle. So insulated, so no heat transfer is going across it. It has a velocity of 50 meters per second on its way in, and it leaves at 150 kPa, 0.15 megapascals. It has a velocity of 600 meters per second. We're going to determine the final temperature if the steam is superheated in the final state, and the quality if it is saturated, right? So it could still be superheated. We're going to presume it starts out superheated, but we're not quite sure right here. So this is a very common problem to look for, but it's got the little complication that it's dealing with steam, so we're going to pay attention to it. Recognize that there's also other things that are very closely related, a diffuser and a throttle, and we'll talk a little bit more about them coming up soon. All right, so let me, and oh, by the way, here's the English version is going to come up in the next video. I need to do that so that you can make sure here's one where the units are going to be really important, so the next video, watch out for that. I know that's just really exciting for you, I can tell. So here's our information. Let's see, did I write anything down beyond this? No, not so much. The main equation that we're dealing with is still going to be this guy right here. I think we're going to go for the total for this. We're going to have the summation of m dot, and we're going to go h in plus 1/2 v in squared. I don't really want to do the potential energy here because I don't want to fit it in. That's okay. I'll make it fit in. I think it's gz in, right, and then minus square root, not square root, summation of m h exit plus 1/2 v exit squared plus g z exit, right? So that's the equation we're dealing with. It's insulated, so nothing crosses this boundary. There's no work crossing the control surface's boundaries right here. So, and we're going to ignore potential energy changes right there. So basically, what we're going to say this is all equal to 0, and that mass flow in and mass flow out are going to cancel out. So we're left with a HI plus 1/2 VI squared equals H, I'll call it E, plus 1/2 VE squared. All right. So that's the big idea behind it. So let's get some information based on our states. You know, we could call that 1 and 2 right there. So now we can renumber these. Instead of I and E, it could be 1 and 2. Let's see. We're going to go for 600 kPa and 200 degrees Celsius. So let's go back up to, presume it's their steam tables. So we'll get to B.1.3 and look for 600. Let's see, did they do us any favors here? Here's 600 right there. Okay. So we'll zoom in on that. And we said that it was going to be 200. Okay, cool. So it's not really all that high. So we have an H right there. Do I need V? I don't think I need V. Sometimes it might be useful if you know the area and then you want to know the volume flow rate, but that's not really done with steam all that much. We might do that with air. So I'm writing down as we're talking that we have 600 kPa and T1, it's supposed to be 1. I may have meant it once. You can't see what I'm doing. I should go back to this right here. Boom. So that's, what is that? 2,638.91. H1 is 2,800 and, did I just say that wrong? I feel like it. How come I did that wrong? Oh, that was it. Once again, I do that a lot. I don't look at the top up here. So don't be like me, kids. Don't be like me. We need to go to the enthalpy and not the internal energy. I did that before. So here's the one I want right there. 2,850.12 kilojoules per kilogram. It's tough sometimes. It's tough. It's a hard road to go down. All right, so we can actually figure this out. All right, I think we can get what the enthalpy is going to be coming out of this thing. So we go here. This is the equation right here. We go 2,850.12, and notice these are kilojoules per kilogram. I'm going to pay attention to my units because it's going to matter here in about 1 second. We have 50 meters per second, and we're squaring them. And you're going to go, whoa, wait a minute. How is that compatible with that? Well, gotta hold on for a second. Let's see. We want to stay in kilojoules per kilogram, but we just wanted to say, do we have to put a conversion factor in there? That's the big question. And we'll try to get to the big answer here in a second. 1/2, and we said this coming out is 600 meters per second, and I'm going to square it, so meters squared per second squared. Well, let's take a look at this is a kilojoule per kilogram, right? Which is going to be a 1,000 Newton meters per kilogram. And that means that's going to turn into 1,000. Remember that a Newton is a kilogram meter per second squared. So you go kilogram meter per second squared, but that was per kilogram. Oh, and times meter. Did I do that wrong? Yeah, Newton meters. So we replace Newton with the kilogram meters per second squared. Right there is the Newton. Right here's the kilogram, and there's the meter. So you see the kilograms coming out, and the meters squared, second squared. All right. So what we have a problem with is that kilo. So we need to divide by 1,000 right here in order to make these compatible. So it's almost worth checking out just for a second, rewriting this down as the individual things, right? So 2,850.12 plus whatever this equals to. So we're going to get 50 squared. Did I write down in between numbers? I did not. I should have written down in between numbers because there's some knowledge to be gained from this. 50 squared divided by 2 divided by 1,000. Right? So we get 1.25. Ooh, that's not a lot compared to this. Go to HE is what we want to try to get. Plus, let's see what this one is. It's probably a lot more because it's 600 squared. 2 divided 1,000 divided 180. More, but not a lot more, right? So anyway, we're going to add that to here. Add the 2,850.12. Add that to 1.25, but then subtract out 180, and you end up with HE should be 2,671.4 kilojoules per kilogram. Now we want to find out if it's exhausting at 0.15, so that's 150 kilopascals. So we're going to go back to, and we don't quite know whether it's saturated or not saturated. Let's go to table B.1.2 and look at P2 is equal to 150 kilopascals and make our decision based on what's in there. So, see, is this the one? Is the pressure entry, but we have the wrong pressure. There you go. So let me get rid of him. So we have a pressure and 150 right there. And so that's important to us, right? So we can see that we have the TSAT. Well, I guess the TSAT doesn't matter in this case. But let's, if we were to ask what the final temperature was, then it will matter, right? So if this works. So I'm on the specific volume page. I have to go to the next page over for the 150 right there. And this is enthalpy. So let's take a look about our enthalpy. Here's the enthalpy of the fluid, and here's the enthalpy of the gas. And sure enough, we were 2,671. We are in between these two, although very, very close to being a gas. So it's very close to being a gas, but or being a superheated, but it's still a mixture that's in between here. So, and they said, well, find the quality. But this is definitely the exit temperature, because this is right now it's in the midst of losing its heat of vaporization, which is this number right here, by the way. That's a really important number, that HFG. That is the heat of vaporization at this pressure and temperature, where it will remain constant at this temperature as long as it's the same pressure right there, while it phases completely from being a gas to a liquid. It's a very important number, very important concept to get to recall the heat of vaporization. So let's see, we'll write all these numbers down, and so add here. So we're going to have an HF equal to 467.08 kilojoules per kilogram, and then HFG. Right? We could write down HG as well if we wanted to, but it's we by inspection we saw that it was going to be, without writing it down. I mean by inspection, we wrote it down like it says yes, a mix. I don't know. Trying to communicate that. So anyway, we can write down our H is equal to HF plus X times HFG, where we write down, we have an exit of 2,671.4. We have 476.08 plus X times 2226.46, right? And so our x is going to be a really large number. 98.99% is the answer. So right here is actually the exit temperature, and right here is the percent. So if you want to write down the answer, T is equal to 111 degrees Celsius, and X is equal to, I guess I'm going to keep all the sig figs as part of that, because otherwise it's going to turn into 99. So, but I guess it's not that bad if you just said 99. So let's see, we're 15 minutes into this. I will also mention that a diffuser is really just going the other way. Generally, the velocity is going to be larger now, right, which is backwards, right? So as a nozzle is usually that direction, it converges. A diffuser goes the other way. And sometimes you have a converging, diverging one where it will converge and then it'll diverge, but it won't diverge back to the original one so much. But this is like, I often think of the diverging one, like an example might be the end of a CO2 fire extinguisher, right? Where you're going to whoosh, and we're expanding out, like out from there, right? As opposed to here's like a garden hose, right? Where we're shooting the thing out, right? So it's just the difference between a nozzle, converging nozzle versus a diverging nozzle, which is called a diffuser. We also have a throttle, which is an important part of a old style carburetor, or the assembly that is creating controlling the speed of an engine. And here they're just showing it as an orifice, but the idea here is the velocity here doesn't change from the velocity here. So there's no kinetic energy difference on either side. So if we go back up to this concept right up at the top, what we find for a throttle is a good thing to remember. The enthalpy in equals the enthalpy out. It's a constant enthalpy. We even call it isenthalpic. Isenthalpic, so it's another name. So for a throttling process, where we're not changing the velocity, the enthalpy stays the same on either side of the thing, which is sort of a surprising thing to find, but it is true. And I think that's all that we want to say for this. I have something else I was going to say. I'm sure we'll come up with it later. Probably. Maybe not.